Hey, what's up, guys? Chung here again. So tonight, let's take a look at this LeetCode problem here, which is number 815, bus routes. Okay, hard. I like this problem. So if we have a list of bus routes, and each uh, route I is a bus route that's basically the route is a kind of list. For example, if the route 0 is a 157, it means that uh, you can travel, right? You can travel to any of the stops, right? You can go to from one to five, from five to seven, and from seven to one. Basically, it means that at any of the stops here, right? You can go to any other stops, right? Within this routes here, okay? And basically, so the first input is a list of the routes. Basically, it's a list of lists, and then you have a start and stop. Okay, basically you start from this stop one, and you have a target basically, and you have a target T here. You want to go to the target stop 6, and it asks you to find the least number of buses, right? We must take to reach our destination. Okay, and return -1 if it's not possible. Okay, so for example, right? So for this one, we start from 1. Okay, and then from 1 to basically we from 1 to we go to 7, right? And from 7 we can go to the other bus, right? We can get on the other bus, and then from the 7 to go to 6, and so the answer is 2, right? I mean, this one, I think it's not hard to think to I mean to realize that this is like a BFS search problem, right? Basically, from at each of the stop, you can go to you can have like different options, right? And you just need to find the basically the minimum hop, right? The minimum hop to get from the start to the target stop. Okay, and that part is not that hard, but the difficulty for this problem is how can we build the graph, right? Or do the BFS search so that from 7 we can go to 6, okay? Right? Because so I mean, I think a naive way is that I mean, basically for each of the stop, right? For each of the stop, we want to see the brute force way will be basically we're creating a graph, right? The graph and the key will be the stop, and the value will be from the current stop. From the value will be a list or a set of all the stops from the current stop to get to without taking to another bus. So which means in this case, right, from 1 we can go to what? 2 and 7. Okay. From 2 we can go to 1 and 7. Okay. And from 7, okay, from 7, sorry. So from 7 we can go to what? We can go to 1 and 2 and also 3 and 6. Okay, so same thing for this 3 here, can go to 6 and 7. Okay, from 6 go to 3 and 7. 7, yeah, 7 is done. 7 is done. Okay, right. So I mean the brute force way will be basically we just loop through all the routes here, right? And for each of the routes, for each of the stop, we're trying to build a list, on this stop, which means the list of stops means that from this stop we can go, right, without taking any of the without moving to any of the bus. Okay, so every time now we have a graph here. Every time when we have a stop here, we just simply loop through. We just need to do a BFS search based on this graph. Okay, I mean, it will work, but unfortunately, it will TLE because of this. As you guys can see, the length of the maximum length of the roots is 10 to the power of 5. And to be able to build this like graph, the time complexity we need will be n squared, right? As you guys can see, basically we are for each of the roots here, and we're looping through all the stops here, and for all the stop, we're adding everything else, right? All the other stops for this stop, for the current stop. That's going to be the n squared time complexity, which will be TLE. Okay. So then this, so okay, so since this one doesn't work, how can we do it, right? I mean, then we notice that, right, the root itself only has like 500, okay? It only has 500. So it means that instead of building like a stop to stop, right? This is like stop to stop relationships. We can build like stop to what? To the roots, right? So basically, I mean, for each of the stop here, right? Let's say, for example, the stop one, and stop one belongs to what? Belongs to root zero, root zero. I'm assuming I'm giving each root like I'm using the index as the root ID here. So basically, one belongs to root zero, and two belongs to root zero, right? Three, sorry, seven, okay, belongs to root zero, okay. Now three belongs to root one, and like 6 belongs to root 1, and 7. Now it's 7 again, belongs to root 0 and root 1. Okay. Okay, cool. So with these things here, right? So now we have a stop to roots. Then we just do the breadth first search from 1 here. Okay. And the way we're using this graph is every time when we have like a 1 here, right? When we have a stop here, we just look for, okay, how many roots this one belongs to, okay? And for those roots here, we just loop through all the stops within those roots, and we add those stops into the queue. That's how we do the BFS search. Okay, of course, we're gonna be using like some visited or seen set to record uh, the stops we have visited and also the routes we have been used before. Yeah, I think that's pretty much it is. Basically, we just move from this O(n) square to this like to be basically to build this kind of the second graph here. The time complexity will be like this one, n times what? 500, right? Cool. So let's try to code this up here. Okay, so first, like I said, we need to create a graph here. Okay, the graph will be a default um, dictionary set. Okay, so for roots, for I and roots, enumerate roots here. Okay, for stop in roots, right? And the graph is this stop belongs to this root. Basically, like I said, I'm using the index to represent the ID of the roots. Okay. So now basically we're building like a graph here. The key is the stop, and the value is a list of the roots this stop belongs to. Okay. And then we have answer equal to 0, and then we have a queue here, right? Then we have a queue collections, right? Dot dq collections. The starting point is s. Okay. Yeah, the s, and then uh So scene stop, okay. Basically, I'm going to create two set here, and the second one is the scene roots, okay. It's also a set, and scene stop dot add s, right? Because that's the starting point. Now let's do a BFS here, okay. For in range length of the queue stop, okay, equals to pop left, okay. If stop equals to t, right, and then we simply return the answer, right? That's the stop, the base case, right? When we have like a stop, when we see the t here, we know, okay, we have find the minimum bus we need, because we have already add everything, right, to this stop here for basically for all the routes this stop can go, okay. So now uh, we have the stop, and the graph we have is from the stop to the routes, okay, which means from the stop we can know what are the routes this stop from this stop that it can go, right. So it means that from the routes, okay, in the graph stop, okay. Mm, and we check, okay, actually, let's not use this scene route first. Let's only use the scene stop to make it easy, right? And then we can try using this like scene routes to optimize our solution time complexity here. So from the root here, right? So from the root, we can get everything. We can get all the stops within this route. Okay. Basically, it means that that's all the stops from the current stop. I mean, we can go freely, right? Without uh without changing to any of the bus. Okay. So for a new stop, okay, for new stop in route, in well, actually, this is the route ID here. Sorry, it's not the route itself, the route ID. And to get the routes itself, we have to do a routes dot route ID, right? That's the stop we can go. And now let's do a simple check. If the stop not in scene stop, okay, then we just uh, append this new stop to the queue, and we also need to uh, add these things to the scene. Okay, yeah, and that's that. And yeah, and I think that's that answer plus one. Okay, here we simply return -1. This should just work, right? Basically, from the current stop, since we have built the relations from the stop to all its routes. Now, basically, what we're doing here is we're adding all the possible stops. From this stop, we can go without changing to and without changing to a um, without taking to another bus. Okay, right? Because if the stop is like the 7, right? So from 7, basically we can either go to 1, 2, or we can go to 3, 6. Okay, yeah. And let's try to run the code. Okay, this one works. Submit. Yeah, as you guys can see, it's accepted, right? So even though it's only faster than the less than 10%, okay, but it still works. Basically, that's the idea here, right? So we're using like this stop to routes graph here, and for each of the stop, we're trying to get all the possible stops from this stop this stop can get to, and then we add that to the graph. Okay, and then we just do a BFS search. So what kind of improvements we can make here, right? So the improvement we can make is the mm, we can also record which route we have processed before. Why is that? Because every time when we have a route here, basically we're adding all the, all the stops within that route to our queue. Okay, so it means that I mean next time when we see a new route, another route that which we have already seen before, we can simply skip that because we know we have already add those stops, right, for to the queue to the queue before. So we can just simply do an early termination. And so that's what I'm trying to say here. Basically, mm, if the route ID not in scene route, okay, yeah, then we do this. And in the end here, we just do a what scene route dot add route ID. Okay, yeah, cool. See, it's much faster. It's only we are basically getting a huge improvement here just because because of this. Otherwise, otherwise we have to be basically looping through all the elements, right? All the elements in this route one more time. For most of the even though for those new stops, we will be a stop, will be a skipping from here if we process a route we have already been seen before, right? But as you guys can see, we will be looping through all the stops in that old route again. So, but if we do a if check here, we can simply save the nested for loops, right? Cool. Yeah, I think basically that's pretty much it is. Oh, and the space and time and space complexity. So, let's see, this is n here, and this is m. Okay, so for this one, right? For this one, it's a it's a n. The roots is we have a m roots, and then for each one we have a n stop, right? So we have m times n here, and how about the BFS, right? So the BFS we will be looping through. Basically, we're looping through all the elements. Okay. Yeah. Basically since we're using like those those like two scenes set here, we're basically looping through all the nodes, right? For the entire. Yeah, and here I'm always thinking it's also like a m times n, right? Basically, that's the total nodes or total stops, right? We'll be having. That's the worst case scenario, the total stops among m routes, and each routes have like n stops. Okay, yeah. So the space time complexity will be O of m times n, and the space complexity is also like since this one is stops, right? Basically, we have this many stops, and the total stop is also like O of m times n. Yeah, I think that should be correct. Cool, guys. I think that's pretty much it is. This one I think is a good problem. Actually, it's at the first glance, you guys may be thinking, okay, it's pretty easy, just the BFS search, right? Yes, you're right, the BFS search, but the hard part is the how can you convert the BFS? How can you construct the BFS search tree, right? Basically, how can you add how can you construct the graph so that every time when you have a stop, you can add all the possible stops, the possible new stops, right? This stop, I mean you can go from this current stop. Okay, yeah, cool. I think that's pretty much it is. Okay, thank you so much for watching the videos, guys, and stay tuned. See you guys soon. Bye bye.